this talk actually is kind of two talks sandwiched together, and it's kind of giving the chronological way that we came up with kind of the approach we're advocating for clustering multivariate categorical data. So I'm actually going to talk about one approach we did which worked very well, but was disappointing in one aspect, and then we actually kind of came up with an extension that actually we're very happy with, which kind of does a lot better in terms of variable selection, which is kind of the key, one of the key things we're interested in, as well as clustering the data. So I'm going to talk about two data sets just to kind of motivate the work. The first one is just a nice small data set that actually I got from Cathal Walsh, who gave a seminar here a few months ago. It's a data set looking at early onset Alzheimer's disease patients in St. James's Hospital in Dublin. There's 240 patients, and for each patient we have a measurement on whether they presence or absence of 6 different symptoms. So hallucination, activity, aggression, agitation, diurnal, and affective. And the medics felt that early onset Alzheimer's disease had subgroups in it, so that not all patients were the same, and that different groups of patients might have different propensity to have these 6 different symptoms. So the presence or absence of these 6 different symptoms. And they even had more information, which is actually, they felt that there was going to be 2 or 3 subgroups within the population of early onset Alzheimer's patients. And they weren't really sure which, so that's actually kind of a question of interest. So they felt that you couldn't treat the disease as a single disease because there was quite a different propensity to have presence or absence in these different symptoms. So that's one data set we're going to look at. So we want to find subgroups within the population. Another data set, which actually, as a researcher from St. Vincent's Hospital in Dublin, landed into my office one day with a problem, basically where he had a number of patients in St. Vincent's Hospital that were suffering from back pain. And basically, they had 36 different presence-absence symptoms for these patients, and there were 464 patients in the group in total. And within physiotherapy, there's a sense that there are 3 different subgroups within back pain. There's nociceptive, peripheral neuropathic, and central sensitization, which is also sometimes called central neuropathic. And he was interested in actually us analysing the data without taking into account that group information. He wanted us to look at the data he had for all of the patients, the 36 categorical variables that are presence-absence variables, and he wanted us to see what groups we found in the data, and then maybe after the event see whether these correspond to the groups that the physiotherapists believe to be present in the population or not. He had analysed the data, taken into account the group structure, and found, these symptoms are very good at predicting which group somebody fell into. But he was wondering, are there more groups, less groups? And if we do find groups of patients that are very similar in their symptoms, do they actually correspond with the physiotherapy groups or not? Now, the collaborator was very easy to work with because he actually had done a lot of statistics courses while doing his master's in public health and epidemiology. So, I mean, he had been using logistic regression, Bayesian methods, Bayesian model everything. So it was a nice collaboration in the sense that he wasn't afraid of some of the more advanced techniques that we did. So again, we have a data set collected from some population, and we want to see, are there subgroups in this population or not? One further thing he was interested in was, could we reduce the checklist of 36 symptoms that the physiotherapists are currently using to a much smaller subset and still recover the subgroups in the population? So there's a variable selection aspect here as well. Can we diagnose patients into subgroups using much less than 36 symptoms? That's another thing you wanted us to look at in the process. So both of the examples that I've mentioned involve clustering, and they also involve potentially variable selection. So can we reduce the dimensionality of the data and still find the subgroups that we're interested in? So that's just kind of, they're my 2 motivation examples. I'm mainly going to talk about the second one, but I'm including the first one so that we have, basically, it's easier to show results for the smaller data set. So just some notation and background. I'm going to analyze this very much as a statistical problem, a modeling problem, and there'll be various aspects of doing inference for the models we're fitting. So we have an n by m data set, capital N patients, capital M variables. The nth observation for subject n is going to be denoted xn, and the way we're going to model the data is using a finite mixture model. So we're going to assume that there are G groups in the population. The probability of coming from group G is given by tau G. So that's basically how prevalent the group is in the population. And then within each group, we're going to use some standard basic statistical model for basically modeling the data within each group. And that distribution will be characterized by some unknown parameter theta G. So theta G tells us about the parameters of the subgroup G, basically. So this is just a standard finite mixture model. So we're going to fit a finite mixture model to the data. We're going to have to estimate the unknown parameters. And one thing we have to spend a bit of time also worrying about is how do we estimate the number of groups? That's something we're going to look at. Now for categorical data, the standard model, the standard finite mixture model that people use is something called latent class analysis. And basically it's a very simple model once you kind of spend the time looking at it for a while. At first it might look a bit daunting, but it's actually probably an overly simple model, but it actually has been shown to work very well in practice. If you were in machine learning, you might call this the naive Bayes model rather than the latent class analysis model. So for each subject, we have m categorical variables. And basically what we do is we assume that once we know what group somebody comes from, the m categorical variables are just independent multinomial random variables. So somebody is going to draw the value of, if you think of it as a data generation process, once you know what group an observation comes from, the variables are independent of each other. And this is called the local independence assumption. And basically, somebody that belongs to group G, for variable m, it's going to take value c, whatever value, because it's a categorical random variable, with probability theta G MC. So theta G MC is the probability that somebody from group G, for variable m, takes the value c. And basically, they're just independent multinomial, or kind of effectively Bernoulli random variables in the case of binary data. These values of theta GMC are going to be very important for telling us the difference between groups, because it's telling you what's the probability of observing category C for variable M for somebody who belongs to group G. And if you had a variable where the value of theta GMC doesn't really vary with G, it's basically the probability of variable M taking value C in each of the groups is more or less the same, that would be evidence to suggest that that variable doesn't actually tell us anything about the groups, because in all of the groups, all of the individuals have the same probability of taking each of the categories. So that's going to be a key thing when we're actually trying to do variable selection. So, but we're basically just assuming that all the variables are independent and they're just multinomial, single draw from a multinomial distribution. So to kind of explain the types of results you get when you actually fit a latent class analysis model, here's the output from an OR package that a former PhD student and I wrote, Arthur White, she's in Trinity now, when it's applied to the Alzheimer's data. So it told us that there were 3 groups in the population. I'm not going to get into the inference for this for the moment. The plot is broken up horizontally into 3 bars, and that's showing us the tau G values. So 2 groups have very large probability, and 1 group has very, very small probability. That's why it's a really narrow sliver. And then we've coloured the bars according to the theta G values, basically. So if you get a white colour, it's telling us there's a high probability of that symptom, and if it's red, it's kind of a low probability of that symptom. And the legend is shown here. So we can see for the first symptom, in all the groups, the probabilities are quite low. In the second group, the probabilities are a little bit lower in group 1 than in group 2 and 3. In the third, for the third symptom, you have a very high probability in this very small group, a medium probability in the second group, and a very low probability in the third group. And you can look across the plot and you can kind of read off what the probabilities kind of are roughly. So it did suggest to us there were 3 groups, but one of the groups has a very low probability, so it has a very low tau value. But if you actually look down any of these bars, you can see, for example, for the first symptom, which was hallucination, all of the groups have a very low probability. So hallucination isn't really telling us about the groups in the population. So if we were to do variable selection, we would probably expect that that variable would drop out of the model, and it would tell us, it doesn't actually tell us anything about the group structure. Where in contrast, say the 5th column, we've very high probability, medium probability, and very low probability. The 6th column, low, high, and kind of pretty high. So we can see this, if you look down any column in this plot, it's giving you an idea of which variables are useful for clustering and which variables are not useful for clustering. Yep.
What information is encoded in the length of the bars again?
The group probability. So the group 1 and 2 have very high probability and almost equal, and then group 3 is just a very, very small.
So maybe I thought you were saying the colour was...
No, the colour is the probability of the symptom given that you come from the group. So yeah.
So there's 2 probabilities you can take.
Yes, yeah. We tried to do it in one plot, and yeah. So the length of the bars is telling us the group probabilities, and then the colour is telling us the probability of presence given that you're in that group.
Is the group probability like a prevalence?
Yeah, it would be basically, yeah. So
a tiny number of people in the upper one.
Tiny number, yeah, very, very small number. Yeah, but it did, a lot of the methods did suggest, we've tried a lot of methods, do suggest you need that third group, though. Even though it's a very small group, you do get a much better modelling if you actually include that third group. To fit a latent class model, there's lots of ways you can do it, but fitting mixture models, basically the most efficient way to do it, the likelihood function for a mixture model is quite complicated, even for a model that's got a very simple structure like latent class analysis. The way we do it usually is we augment our data with a variable that basically tells us which group each observation came from. If we knew what group each observation came from, our likelihood function simplifies hugely because it becomes a whole load of products. So when we're fitting latent class analysis model, either in a traditional maximum likelihood framework or in a Bayesian context, it's really common to augment your data with this extra variable that tells you what group each observation came from. It's an unknown quantity which we're going to have to kind of infer as we proceed with our algorithm. But when we do that, the likelihood becomes much, much simpler, and that's going to really help doing inference for these models. So that's just one thing. I'm kind of getting into some of the technical background of what goes on behind. How do people fit latent class analysis models? The most common way is to use the EM algorithm and to find maximum likelihood estimates of the parameters. Some people have done variational Bayes methods as well, and you can do MCMC as well as another option. Most of the methods assume that you know G, the number of groups, and the way you estimate the number of groups is you fit a model with 1 group, 2 groups, 3 groups, 4 groups, all the way up as far as whatever you think is the maximum plausible number of groups, and use some criterion to choose the number of groups. There are some previous Bayesian approaches using, say, really complicated reversible jump MCMC methods that will actually infer G directly as an unknown parameter in the model. So Silvia Pandolfi, Francesco Bartolucci, and Niall Friel had a paper where they developed some reversible jump MCMC algorithm for fitting latent class analysis models and estimating G simultaneously. But it's quite an involved process to do it. Now we're going to be taking a Bayesian approach fitting latent class analysis models, but we also want to do variable selection. So what we're going to do is we are going to partition the variables in our model into 2 sets. We're going to say that some variables are useful for clustering and some variables are not useful for clustering. So new CL is just an index the index of all the variables that are useful for clustering, and nu n are all the variables that are not useful for clustering. So we're just partitioning the variables. These ones are good for clustering, these ones are not. And so we're going to take the latent class analysis model and change it a little bit now to do variable selection in latent class analysis. So we're going to model the two parts of the data separately. For the variables that are useful for clustering, we're going to take the original latent class analysis model as before. For the variables that are not useful for clustering, all we're doing basically is we're going to make, I mentioned these thetas before, we're going to say that theta GMC is equal, it doesn't depend on G. And we've changed the notation that we denote the common value for theta GMC, it no longer depends on G, by rho, basically. So we're going to say for some variables the thetas vary across groups, for other variables they don't, basically. And we just used a different letter for for observations where it doesn't. And that's the common probability. So if a variable is useful for clustering, this will be the contribution to the model, and for the variables that are not useful for clustering, this will be the contribution to the model. Because the thetas don't depend on G, the top term simplifies a lot, and it becomes what we have written here. We're going to what we're going to do is we're going to, like the Pandolfi, Bartolucci, and Friel approach, we're going to try and fit the model using a Bayesian approach and explore the space, basically the number of groups and the space telling us which variables are useful for clustering and which ones are not, using a Monte Carlo algorithm. So we put prior distributions on the model parameters, all the model parameters, and we use conjugate priors to simplify calculations a lot. But we're going to do something a little bit differently in a second. We also put a prior on the number of groups, and to discourage a large number of groups, we're actually using a Poisson 1, a truncated Poisson 1 prior on the number of groups. Well, truncated to be between 1 and some maximum value. So that's to try and discourage unnecessary groups being added to the model. And we have to put a prior distribution on which variables are good for clustering or not. We just basically put a Bernoulli random variable for each variable, whether it is a clustering variable or not, in advance. And we found that actually just setting it to be a Bernoulli, a coin toss a priori, whether a variable is useful for clustering or not, did quite well. We looked at more complicated alternatives and didn't get much benefit. Now, once you put together all the parts of your model, your likelihood and all your priors, you get this absolute monster of a equation for your posterior distribution. That's really, really tricky to handle in practice with your calculations. So the posterior distribution for all the model unknowns, given all the model knowns, actually has this really complicated form. And we could have developed an MCMC algorithm to fit the model in practice, but it would have been a lot of work, and it would have involved a lot of complicated tuning of the algorithm to get it to explore the space efficiently and things like that. So we actually didn't do that. What we noticed was, that I think when people go down the Bayesian route, sometimes they get a bit lazy and they get totally caught up in trying to come up with a MCMC algorithm that explores the space they have. It turns out that the posterior distribution that we have, even though it's really complicated, and when you're doing MCMC, you're trying to integrate out things basically using Monte Carlo approaches, you can actually integrate out a lot of the parameters in this model analytically just by sitting down with a piece of paper and going through the maths. And the maths isn't even that difficult. So you just need to be good at doing your integration. But it turns out that you can integrate out almost all of the parameters in the model and drastically reduce the dimensionality of the space that you're trying to explore with your Markov chain Monte Carlo algorithm. So we actually basically found that you can integrate out the thetas, the rhos, and the taus out of the model, and leave yourself with a posterior distribution for the number of groups, what group each observation comes from, that's what the Zs are recording, and our new vector which tells us which variables are clustering variables and which variables are not. A useful thing about this is it's actually a much easier thing to sample from, and also its dimensionality is fixed. If we had actually left the thetas, the rows, and the taus in the model, every time you add a group, the dimensionality of your parameter vector increases, or if you remove a group, it decreases. So it's a much more complicated thing. So we basically, by sitting down and actually doing some maths by paper and pencil and on the whiteboard, you can simplify your posterior hugely. Now, it does have a messy expression, but actually it's very easy to compute. The posterior distribution involves computing lots of gamma functions. But it involves lots of products and sums. And it's very straightforward to do, basically, in practice. And we basically then were able to generate an MCMC algorithm that explored the space that told us how many groups are in the population, which observations belong to which group, and which variables are good for clustering or not. So we developed moves that basically allowed us to explore that space. And this is very like an approach proposed by Agostino Nobile and Alistair Fernside, basically called the allocation sampler. Basically, that's what we basically have developed for this latent class model, which also includes variable selection. So we had developed all these moves, which I won't go into in a massive amount of detail. We had moves that allowed you increase the number of groups, decrease the number of groups, and then move a variable from being a clustering variable to a non-clustering variable to get a sense of which is the right model for the data. I'm actually going to skip that bit. One thing that the algorithm loses is we've integrated out the thetas and the rows and the taus out of the model. We came up with a way of at least getting estimates of the posterior mean for the thetas, the rows, and the taus, using actually basic rules of conditional probability at the end. So basically, we're able to take the output from our MCMC and recover the posterior distribution for those parameters we'd integrated out at the end, using basically the standard rules for working out expected values and variances, using kind of conditional expected values and conditional variances. And again, the algorithm basically, this is just a trace plot of the log posterior as the algorithm ran, and it's exploring the space quite well. And when you look at the, this is looking at the model kind of selection idea, a different plot. It's suggesting to us basically, the color is telling us what is the probability, it's trying to represent what's the probability a variable is useful for clustering or not. And we're also trying to represent the number of groups using this heat map. So any region of the plot where you've got kind of a bright color, it's telling us those variables are useful for clustering, and that's some indication of what the right number of groups is. And the model is telling us there's quite a strong probability of there being about 70% probability of there being 2 groups, a bit less for 3 groups, and a very low probability of 4 groups. And it's telling us that variable 1 is not very useful for clustering. So it's telling us you can get rid of that hallucination variable as far as clustering goes, and there's quite a strong probability for 2 groups. In fact, it's about 63% probability of a 2-group model, a 30% probability of a 3-group model, and about a 6% for 4 groups, and it goes down beyond that. So it's telling us, it's actually saying that the strong evidence of 2 groups is sufficient for modeling the data. And we get the group probabilities then given here as output. We actually ran, this is our algorithm and our kind of using the conditional expected value and variance formula to get estimates of the parameters in the model for the thetas using our ad hoc approach. And this is what you would get if you used an exact algorithm that was much more complicated to code. You actually get very similar results. our algorithm was much more efficient, and we got very similar estimates. And, and you can see that's the results we got. When we ran this on the back pane data, we got kind of similar results in a sense. It told us when you analyze the back pane data, it's telling us there's very strong probability of there being 7 or 8 groups, and it's telling us that one of the variables is not very useful, so you can get rid of one of the 36 variables. And we were kind of disappointed by this in a sense. We were hoping to get rid of a lot more than one of the 36. So this is kind of the first part of the talk, in the sense that, and just to show you, the groups do correspond quite well with the physiotherapist groups, but we're kind of subdividing their groups. So the central neuropathic group, the neuropathic and the peripheral, or the nociceptive and the peripheral neuropathic groups are being recovered, but we have extra clusters. We're subdividing them into smaller groups, which may or may not make sense. I mean, the physiotherapist, when he was shown the results, was able to come up with a story behind why we were finding subgroups. But sometimes you wonder, are they doing that just to enforce the results you found? So we're very happy with the approach up to now, because it found the groups and we were able to do variable selection, but it wasn't giving us very much variable selection. And that led us to think, are we doing something a little bit wrong, or is there something in our model that's making us not get very much variable selection? And it turned out that basically a lot of what's going on in our model is actually, the problem is a lot of it's to do with the local independence assumption that we have. So we actually took a step back and went back to some other approaches basically to try and resolve this. So I'm actually going to take a very different modeling approach in a second to answer the same question, but maybe get us a lot more variable selection. Now, the local independence assumption in the model that I have here, the reason that we're not getting very much variable selection is the following. Because we're assuming the variables are independent within each group, once we know the group memberships of the observations, the model selection that's going on, no matter what approach we take, be it classical or Bayesian, when you're deciding whether a variable is useful for clustering or not, it's making that decision independent of the other variables. So if you have two variables that contain the exact same information about the clusters and the data, both of them will be included, because each variable has a different prevalence across the different groups. And basically, what we decided was that that's not really a good way to proceed with things. What you want to do is, when you're deciding whether a variable has clustering information or not, you want to make that decision taking into account which variables you've already decided are useful for clustering. And you want to decide, does the variable have extra clustering information beyond the current set of variables you're using? So we actually took a step back to an approach for variable selection in the latent class analysis model that was proposed by Adrian Raftery and Nima Dean a few years ago, where they developed a greedy search for which variables are good for clustering and not clustering in a latent class context. So when we have our data vector, the M variables, we're going to partition it into three sets. We're going to have the set of variables we currently consider to be clustering variables, the variable we're proposing to add to the set of clustering variables. We want to decide, should we add it to the set of clustering variables or not, and then the other variables. And I'm kind of use less equations in this part. They decided that the decision on whether you should add a variable to the model should be, again, based on some sort of statistical model selection approach. So you're going to compare two competing models in their approach. This is the clustering variable, the Zs, which tell you which groups each observation comes from. If the variable is useful for clustering, this is a graphical model trying to explain the model. For the clustering variables, they're directly linked to Z. So the clustering variables depend on Z, and the proposed variable depends on Z. And then we're going to say that the other variables are conditionally independent of Z, given the clustering and the proposed variables. They compared that to a model where there's no link between Z and the proposed variable. So that's telling us the variable Z has no information about the proposed variable. And they constructed a greedy search algorithm for finding the best model, basically, to model the data. And their approach, if you apply it to the data sets I talked about, gives you more or less the same results as the method I just talked about. What we did instead is we changed the second model to try and actually get more variable selection. So we said, rather than comparing this model to this one, what we're going to do is we're going to add an edge to the graphical model here. So the first model we're allowing the proposed variable to depend on the current set of some subset of the current set of clustering variables. And basically, we're going to do a model selection between this model and this variable that basically, there is no link between Z and the proposed variable directly, but there is potentially through the current set of clustering variables. And the model selection, once you add that edge to the model, it changes things hugely. The model selection is basically deciding, does this proposed variable have any extra information about the clustering beyond what's in the current set of variables you consider to be clustering variables? And if it does, you'll add it to your model, basically, and you proceed along the way. We came up with a stepwise algorithm for searching the space, basically, of which variables are clustering and which ones are not. And it was basically a standard stepwise regression, or stepwise algorithm. We had a step for adding a variable, removing a variable, and it worked quite well, but it kept getting stuck in local maxima. So we actually found that adding an extra step to our algorithm that allows you swap. So take one of the variables you currently consider to be clustering and the proposed variable and swap them. Don't do an add or a remove, do a swap. And that actually avoided the local maxima problem. And we did model selection using BIC like Dean and Raftery did. Once we changed the model and the algorithm to do this, now these rows aren't all comparable, but basically we found that the last row of this table is the most interesting. The best model we got for the data had only 11 of the 36 variables and actually found 3 groups in the data. So basically, the algorithm suddenly got 3 groups. This is for the back pain data, and it removed 25 out of the 36 variables instead of only 1, which we had previously. And the adjusted rand index suggests that the groups we found correspond quite closely to the physiotherapy groups. That's just showing you a run of the algorithm. It's adding and removing variables and swapping variables. When you do a table of the 3 groups we find using our 11 variables and the groups the physiotherapists previously felt were there, there's quite a strong connection between the two. Furthermore, there is some mixing between what we call group. The nociceptive patients seem to be split across 2 groups. And when I went to talk to Keith, the physiotherapist who was working on this, he said that makes sense because a lot of patients will actually have both nociceptive and peripheral neuropathic pain, not just one or the other. And maybe actually, you know, the physiotherapist had to make a call on which pain type was dominant, basically. And maybe they got it wrong, or maybe because both are so prevalent, they actually are genuinely in both groups. So there's quite a lot of correspondence between our approaches. We then, within each group, for the 11 symptoms, we have the prevalence of whether somebody had the presence or absence, basically. And we can see, if you look down every column of this plot, unfortunately I don't have the bars broken up by group probabilities. This is from a different student who worked on this. You can see that the colour changes as you look down each group. So the 11 symptoms that were left in the model do have very different probabilities of presence and absence as you move across the 3 groups. So the 11 variables that are left all seem to have evidence of clustering. And these are the probabilities and the names of this. Like, this is actually a description of the symptoms. Now, there was a slight problem with this analysis in a sense that sometimes I find when you're working with an applied researcher and you do a lot of variable selection, and given that the variable selection approach is saying we're not going to include a variable if it has no extra information about the clustering beyond the 11 variables that are here, sometimes the applied researchers can get lulled into a false sense that the 25 variables that I've removed from the model have no group information in them. But that is not the case. We're saying that you get just as good a clustering with these 11 variables as if you had all 36 variables. The other 25 variables are effectively redundant. They may have group information, but that information is redundant relative to these 11. And we wanted to make sure that they didn't feel that the other 25 variables were irrelevant. We're just saying they're redundant. They don't have any extra information. That was the key thing. So we tried to come up with a way of trying to present this to the physiotherapists so they would get this point. And what we did is, for each of the 11 variables that we had, we basically ran a logistic regression on basically each of the discarded variables, which are the rows, versus each of the selected variables, which are shown in the column of this plot. And we coloured the square according to the value of the likelihood ratio test, basically to see whether that the coefficient in the logistic regression was significant or not. So if you have a dark square, it's telling you the discarded variable is very strongly related to one of the clustering variables that's been chosen. And you can see there's a lot of blue in the plot. So it's basically trying to get across the point that the discarded variables are actually, they do contain a lot of similar information to the variables that were actually kept in the model. There are some exceptions. For example, there's one row here that's almost entirely white. That's the variable that was dropped by all the approaches. It just doesn't seem to have any group information at all. And basically, but all the other rows have some sort of blue in them. So all of the discarded variables, in some sense, do depend on the 11 chosen variables that were left in the model. So we've proposed a statistical model-based approach for clustering data that also includes variable selection, and we've got very good results in terms of recovering the groups. And the second approach got a lot of data reduction. It really reduced the number of variables, and that would drastically reduce the number of variables the physiotherapists would potentially have to record from 36 down to 11. The first approach did very well and explored the model space very well, but it didn't get very much data reduction. But we found that was because of the model assumptions to do with independence. They were probably overly restrictive, and as a result, not enough variables got discarded, because the decision on how the variables were discarded or not was quite different in the two modelling approaches. So that's basically where we are, and if you have any questions, I have some spare slides that show you the results on simulated data, but we can look at them if we want after. But that's great.
So open it up for questions.
Yeah.
You used essentially a local search algorithm.
Yes.
For that last method.
Yeah.
I mean, how confident are you with the results, given that? I mean, if you ran it a lot more times, could you get rather different results?
That's why when we had the original search algorithm was just add a variable, remove a variable, and we were not at all confident about our results at all. Like, you run it from different starting configurations and you got totally different results. Probably equally good results in terms of clustering and maybe a bit of data reduction, but they were just different variables were being kept and removed. So we weren't very confident, but that swap move seemed to really help a lot. And we've actually tried it on a lot of variable selection methods. In statistics, most variable selection methods that involve stepwise consist of adding a variable, removing a variable. Those as the only two moves. But we found, even in a regression context, having this idea of take one of the variables you currently consider to be useful and one of the variables you currently consider to not be useful and swap them and see whether you get a better fit or not. That really, really improved the results in terms of stability. We consistently got very, very similar results from totally different starting values. So we're quite confident actually that the results are quite stable now, where we weren't previously.
Is it purely hill climbing? As in, are
yes.
you only allowing moves that
Yes, yes.
So you're not using any random...
No, we're actually, no, we didn't do any sort of, simulation annealing, or anything like that. No, we're taking a greedy approach. But the three moves seem to help a lot. And we started with very different configurations and still get to the... but there is probably scope for, possibly exploring the optimization algorithm for sure. We were very happy with the results we got even with such a simple local kind of improvement kind of type moves. We were very happy with them. Yeah.
Would you argue for collapsing highly correlated variables down to like a representative variable, or do you think the summary showed at the end would?
Yeah, I think there is merit in something like that, in the sense that when you do variable selection in the way we're doing, it's either in or out. It's a very discrete move, and that actually makes some of the the Monte Carlo algorithms can find it very hard to move because it is an in or out thing. Where if you're collapsing variables or combining them in some way, it's a more continuous move, so you might actually be able to explore the space much better and get better combinations. When you start collapsing variables, you can lose interpretability. The in or out thing helps, but there's definitely scope for that to allow a more smooth move. Basically, yeah. So there's definitely that is a possibility. Yeah, great. Yeah.
Maybe somewhat related.
Yeah.
Just in terms of appreciating the number of groups. I mean, traditionally, I suppose people might do an in-kind of multivariate data set, calculate principal components, and plot the data in that way. And
yeah.
I know there's issues with categorical
yeah.
data, but in these data sets, does it confirm the number of groups anyway?
Doing some sort of categorical version of principal components.
I mean regular principal components.
I can't. We did look at it. I'm trying to remember actually. Yeah, I think it does. It does help. Like it does confirm. Yeah, 2 or 3 in the case of the. In the case of the back pain, or in the. Definitely 2 or 3 in the case of the early onset Alzheimer's, and it's a bit messier if I remember in the back pain data, but it would give you some idea, yes.
I mean, you have as maybe a related issue.
Yeah.
The point is that you at some point have to specify a prior for the number of groups.
Yes.
In your data set.
Yeah.
And a technique like that might sort of give some sort of a priori sort of assurance about the reasonableness of that. Of that assumption. But the kind of second question about the prior which was, do you know what will make your algorithm fall apart?
Do I know what would make our algorithm fall apart?
Are there configurations of data that will make?
Well, if you had the model still assumes local independence within clusters, like the clustering variables are independent of each other. Once within a cluster, and we kept that assumption because that's what people want in latent class analysis. They want groups that within the group you can make this independence assumption. So if you had some very strong it's easier to visualize in a continuous data space. If you have like clusters where there's very strong correlation within them, then we will overestimate the number of groups, for sure, basically, because we'll find small enough groups that the local independence assumption holds. So that's one thing that would break the algorithm for sure, is if that the local independence assumption is quite strong.
Well, I suppose you could be a bit more.
Yeah.
I suppose the latent class assumption might also be something that may not be there at all.
Exactly.
And I was just wondering, you've kind of described something which is sort of describing or representing the joint distribution of the observed data as a mixture. Yeah. And so if you look at even a one-dimensional context, in which a probability density might be expressed as a mixture, but there's a lot of probability densities that could not be expressed as mixtures, and so the assumption of the latent class.
That's true.
Pretty fun, or mixture itself is fairly fundamental as well.
Yeah, or even it's effectively you can represent it as like it might be actually more a continuous mixture. It's like a convolution, and then we fit a latent class analysis, so it's kind of artificially finding groups where it's something more continuous. Like you could argue the mixture assumption. This might even be evidence against the mixture assumption to some extent, that this group, the patients that seem to be mixed up here, it's saying you're fully nociceptive or you're fully peripheral neuropathic. The mixture, the latent variable Z assumes that you're fully one or the other, and you can't be a mix of both. So, you could go down some of these models that allow people to be mixed across groups. It might be more realistic. There are patients that are probably both nociceptive and peripheral neuropathic, and might even be like 80% one and 20% the other. But our model says no. In reality, you're fully nociceptive. You're fully belong to one of these groups and one of these groups only. Okay, our model output might say we're not sure which group you belong to, but the model says you're fully in one or the other. So yeah, no, that is true. So yes, we are assuming that you can model the population using a mixture, which could be the case. It may be the case that you can't do that. So yeah, that's true. Yeah.
I wonder what case where you have a really large number of variables, but your number of cases then is insufficient to figure out the variables that are important. You end up with lots of spurious results.
You have to be very careful, yeah, because if you've too many variables and very few observations, yeah, you're basically going to, the algorithm actually will start throwing out loads to start with. You can't start with, we found the algorithm is most stable if you start with everything as a clustering variable and work backwards. That's computationally less efficient, but it's much more stable. So it'll find a small subset of the variables, enough that it can estimate, from the sample size you have. That's what will actually happen. And it won't allow you add any more because you just don't have enough data to tell you to add them. Yeah, that's what would happen. Yeah. Great.
Do you know what would happen if you chose to use something else than BIC?
We've just been using BIC here. We could use other, we just found it worked well in practice. That's basic. It was a pragmatic decision. I mean, the use of BIC for model selection for mixtures, the classical theory fails. There is a lot of theoretical support since that has shown that it is consistent for choosing the number of groups. But then once you start adding variable selection in again, you're kind of stretching those results, kind of saying, look, we think it's still okay. But yeah, just our practical examples and simulations, and empirical results seem to suggest it works well. But the classical theory for justifying BIC does not apply. The likelihood is very unusual for mixtures when you're choosing the number of groups. But there are consistency results in the literature justifying its use. Yeah.
And these models, I assume they're mostly based on, say, cross-sectional data at one point in time. And could they be adapted to incorporate outcome data so that you could have an iterative
people have done mixtures for longitudinal kind of data where you'd have people recorded over time. But then you'd actually have to decide, do you want people to be allowed to move between groups over time? Would you have to get into something much more complicated? Or do you want to assume somebody belongs to the same group and the groups capture kind of...
If you did that, so if you did your latent transition or whatever, would you then have the same clustering variables at both time points?
See, it gets very, very complicated to decide. Yeah. And it may depend on the application, whether you want to assume the groups are capturing the full profile of somebody or you're allowing somebody to move between groups over time. It becomes much more tricky. Great. Yeah.
Have the results had an impact at the clinical level? Would the physios now be using 11 variables rather than the original 36?
Not yet. Yeah, they were very interested in the results. They were actually very surprised they could get down to as few as that, because the original kind of battery of 11 variables was chosen to be quite good at separating these three groups, which is why we didn't want to use that information to some extent in the original analysis. We're just comparing our results to theirs. So, they felt that all the variables were useful, but I suppose they hadn't been thinking about this redundancy idea. So they weren't surprised when we only removed one using the first approach, but then when we got it all the way down to 11 and still were getting good clustering, they were more surprised. But it is a case of just redundancy. Two variables are recording the same thing, or this one variable is capturing the same as these other two. So they were surprised.
And obviously, so this is really useful, say, if you're trying to design or refine instruments for research, like we do it for us. We've done, say, dietary questionnaires. It can be a case of one where our standard food frequency assessment is actually very, very long, and people have tried various short forms and so on.
No, so they were surprised in one sense that we got it that low, but but it does come down to the redundancy kind of idea that the other questions are useful, but they don't have any extra information about the groups yet. I think they were surprised that the 3 groups came out so strongly, tallied with what they believed in advance. That the 36 questions are actually very good at kind of grouping the patients into, like, grouping them into groups, and those groups actually do correspond to the 3 kind of clinical groups of interest. This table was probably the thing they were most surprised about, I think, but they were so similar.
Did the method work for the Alzheimer's?
It just drops the one variable, so kind of the 2 approaches give more or less the same. So you need the 5. So hallucination is the only one that gets dropped, and that's got very low prevalence anyway in all the groups. So great. Excellent. Thank you.
Thank Brendan again.
Yes.